In this lecture, we are going to learn higher derivatives, and then we are going to learn some application of the partial derivatives. So the higher derivatives are just the derivatives of derivatives. It's just that here we are having partial derivatives since our function are multivariable. Just like the single variable functions, when you take derivative once, you get a new function which is a derivative function, but still it's a function. You can take derivative on function again, and then you get second derivative. You take derivative twice, you get second derivative. You take derivative 3 times, you get the third derivative, right? With triple f triple prime. Now with multivariable functions, we are going to have partial derivatives, but still you can take derivatives twice. Then there will be the issue, the variable that you are taking derivative with respect to could be the same or different, right? So if f is a function of two variables, the first round you can take take the derivative with respect to x or y. The second round, again, you can take the derivative with respect to x or y. So in total, if you have a function of two variables, you will end up with 4 second partial derivatives, which are these 4 that you see. Well, again, these are all the different notations that we are having for our second partial derivatives, but the idea is pretty much the same. Notice that when we write fxy or f12, okay, so here when we write fxy or 1, 2, we take the derivative in this order, x then y. So take derivative with respect to x, then you will take derivative with respect to y. It's really, you find your derivative of f of x, then you find the derivative of f of x with respect to y. See? And similarly, instead of xy, if you use 1, 2, you will have the same thing. F12 means having the original function f, you take derivative with respect to the first variable, then whatever you got, you take derivative with respect to the second variable. And for that reason, the order matters. Okay, so you want to write the first variable and then the second variable, because your f will go this way or z will go this way. So you sort of like go backward when you are writing the partial symbols instead of the sub-index symbols. Okay, so our first example, we are going to find all the second partial derivatives of fxy equals x third plus x squared y third minus 2y squared. In order to find the second partial derivative, you need to first find the first partial derivative, then take derivative on top of the derivative. So f partial x will be 3x squared. X is the variable, so y third is the coefficient, times the derivative of x squared, that gives you 2x, and then the 2y squared will be constant, minus 0. And this will be 3x squared plus 2x y third. That's my fx. Then I will have my fxx, which is this function taking derivative with respect to x. That will be 3 times 2x plus 2y third will be the coefficient of times the derivative of x, which is 1. So I'm having 6x plus 2y third. Then fxy, I'm again taking derivative on this function, but with respect to y. So 3x squared is constant, I get 0, plus 2x is the coefficient of y to the third power. Taking derivative, I have 3y squared. This gives me 6x y squared. These are the two second partial derivatives we get from f partial x. Now start over. For the next two, we need to first differentiate with respect to y. Differentiate the original function, of course. So x third, y is the variable, 0 plus coefficient x squared times the derivative of y third, 3y squared, minus 2 is the coefficient. Derivative of y squared gives you 2y. So this is 3x squared, y squared, minus 4y. Then I take derivative with respect to x on this thing. With respect to x. So 3y squared is the coefficient of my x squared, taking derivative 2x. And the minus for y, the whole thing is constant, so I'm having 6xy squared. If I take fyy, which is this function taking derivative with respect to y, I would have coefficient 3x squared times the derivative of y squared, 2y, minus 4, then derivative of y, constant 1. So this gives me 6x squared y minus 4. And we got the 4 second partial derivatives. Okay, 1, 2, 3, 4. Example 2. Again, we are finding the second partial derivatives of all these functions. F of xy equals log 3x plus 4y. So taking derivative with respect to x, fx will be, first you take derivative of log. You have 1 over 3x plus 4y. Then you take derivative with respect to x of the inside, right? The derivative of 3x plus 4y with respect to x would be just 3. So I'm actually having, since I'm going to differentiate this thing later, I'm going to write it as the power form. So I'm having 3 times 3x plus 4y to negative 1. The power form is easier to differentiate. Now take derivative with respect to x. On this, I'm having coefficient 3, and then I general power rule or chain rule, whichever way you call it. I bring my coefficient exponent to the front. I lower the power by 1, and then I follow by the derivative of the base, where I'm again 3x plus 4y is the base, and I'm taking derivative with respect to x, so I'm having 3. Well, or 3 plus 0, 0 for the derivative of 4y. So this is negative 3. Well, sorry, actually negative 3 times another 3, negative 9. 3x plus 4y to power negative 2. Now fxy, I go back to this function and I differentiate with respect to y. So I take the coefficient 3, I bring the exponent to the front, I lower the power by 1, and then I followed by the derivative with respect to y of the base 3x plus 4y. That would be 4. So I'm having negative 12, 3x plus 4y to negative 2 power. Now for the y side, f partial y will be the same thing. Log gives you 1 over the input 3x plus 4y, but you are taking derivative with respect to y, so you'll have a 4. This is 4, 3x plus 4y to negative 1. Now I can take another round of derivative of x. So this will be 4, exponent to front, power lowered by 1, and then differentiate the base with respect to x, 3. This is negative 12, 3x plus 4y, negative 2. And the last one, fyy, I'm taking derivative on this with respect to y. So 4 is the coefficient, bring the power to the front, lower it by 1. followed by derivative of the base with respect to y, that's 4. So this gives me negative 16, 3x plus 4y, negative 2. The four higher, second partial derivatives are negative 9, 3x plus 4y to negative 2, negative 12, 3x plus 4y to negative 2, negative 12, 3x plus 4y to negative 2, and finally negative 16, 3x plus 4y to power negative 2. Maybe you already noticed that for both example 1 and example 2, the two partial derivatives fxy and fyx are actually the same. So actually we have this theorem saying if f is defined and if you have like a neighborhood, which means something bigger than the point, okay, you need a degree 2 domain. If you have a disk that contains the point such that fxy and fyx are both continuous, then they will agree at the point. So you need a little bigger than just the point to make them continuous. If they are continuous on a range, then they will agree. Okay, so in both of the cases, the first example, the whole thing is polynomial. Their fxy and the fyx are defined and continuous in the whole domain. Similarly, in this example, although we have a bad number, if you look at fxy and fyx, 3x plus 4y can't be 0, but 3x plus 4y was the input of your log, which can't be 0 at the first place. So in both examples, actually fxy and fyx are continuous, not only in a neighborhood of a point, actually it's continuous in its whole domain. So you have fxy equals fyx. But you compute it, whatever it end up with is whatever you end up with. So don't worry too much about, on one hand, you can't really know if the derivative is continuous unless you compute it in most of the cases, unless it's a polynomial, right? On the other hand, I think taking the second derivative is not such a hard thing, so we still want to do fxy and fyx separately, because when they are not the same, you would want to worry like, I probably got something wrong. It's a good thing to double check, and you need to get 3 or 4 partial derivatives anyway. I don't think, cutting this one is a very useful, like it doesn't save you a lot of time, but meanwhile you lose the chance of double checking, and also you are risking the chance that actually they do not agree at certain cases. Okay, now you can pause the video and try practice number 1. Next, we are going to talk about some applications of our partial derivatives. The first one, the tangent planes. When you are having a surface to describe sort of its direction at certain point, you have a tangent plane. Okay, it's easy to say, like you have a surface at this point, you sort of like look at the plane that actually goes exactly the same direction as sort of the surface, but it's hard to really define it. And here's what it is, as how we really define it, like describe this plane mathematically. Suppose we have a surface and it has the equation z equals f of xy. So it's a surface, which means you are having a degree 2 function where you are having 3 variables in total, and the equation itself take away a function, take away a dimension. So you are having degree 2, dimension 2 object surface. Now, if f is continuous, if f have continuous first partial derivatives, okay, which means fx and fy are both continuous, and you pick a point P on S, in the input of the function would be a and b for x and y, then the third coordinate of this point will be z equals f of xy, or f of ab in particular. Okay, so P is the point with x equals a, y equals b. Now you are going to have the curves sort of the same way we defined our partial derivatives. You intersect the plane with the vertical plane y equals, well, sorry, here's a typo. It's supposed to be y equals b and x equals a with the surface. So you slice the surface at, sort of perpendicular to the y-axis and then perpendicular to the x-axis. They will intersect the surface with a curve, and those curves are my C1 and C2. Both of the curves pass through my point AB, FAB. Then I let T1 and T2 to be the tangent line of these two curves at P. Then you have these two tangent lines. When you have two lines passing through the same point, you have a plane. And that is the tangent plane we're talking about. Okay. So the tangent plane to the surface at a point P is defined to be the plane that contains both tangent lines of T1 and T2. And very importantly, it has the formula z minus the z coordinate of the point FAB equals the sort of the direction of the vector will be, well, the sort of the direction of the plane, okay, because you don't have everything on the same side. For x, you have f partial x. For y, you have f partial y. But notice that z is on the left-hand side. So actually, you are not, the normal vector would be fx, fy, negative 1. And yep, that is the formula. Oh, sorry. For each of the points, of course, you do x minus x coordinate, y minus y coordinate, and on my right-hand side, I have my z minus z coordinate. Okay, now let's try it with one function, f of x, y equals 4 minus x squared minus 2y squared, and here we have the point 1, 1, 1. If you remember, this is what we did with our partial derivative example. So, well, what do you need? Fx, f partial x is 4 give me 0, and x squared give me negative 2x, and the negative 2y squared give me 0, so that's just negative 2x, which means my fx evaluated at 1, 1 would be negative 2. Notice that my function are two variables, so the third one doesn't go into my function. That's the output. Similarly, my fy, f partial y, will be, well, 0 minus 0. 4 is constant, x squared is constant when I'm differentiating with respect to y, and I have the negative 2 times y squared give me 2y. So negative 4y, which means f partial y, evaluated at 1, 1 would be negative 4. Well, negative 4 times 1, which is negative 4. Maybe that's clearer. then the whole plane will be z minus this one equals the sort of the coefficient of x minus this one minus 4. Okay, that's the sort of the direction vector of y, not vector, but the coefficient of y minus the y point. That's our formula. Okay, so that's the plane. That's the equation of the tangent plane. If you move this constant to the right hand side, or maybe I should point to the formula. When you move this constant to the right hand side, actually you have an sort of an expression of z equals a number f of ab plus two linear terms of x and y. We started with x squared and y squared, we ended with x and y, right? So this formula would be called the linearization of f at AB. This normally is true when you are very close to the point, okay? But when you are far away, remember you are getting the, what you are getting is the equation of the plane. So it's the yellow plane, but your function is the blue one. So the further you are from the point P, the sort of the more error you have by using the plane to represent the, using the plane, okay, as in this formula or this formula to represent the surface blue. Okay, but we're at the point 1, 1, what you will have is L of xy would be, you just bring the 1 to the other side, 1 minus 2 x minus 1 minus 4 y minus 1. I multiply out and combine the constants. I would have negative 2x minus 4y plus 7. So this is a very easy thing to compute compared to the 4 minus x squared minus 2y squared. But remember, it's true, or it's close. It's a good estimation or a good linearization when you are very close to AB, and when you are far away from AB, you are losing the accuracy. So instead of saying it's a linearization by calling it L for linearization, we call f of xy approximately equals to the same expression, the z coordinate f partial x as the coefficient of x side, and then the f partial y to be the coefficient of the y side. Okay, when you write it as f, it's a linear approximation. Linearization is like, it is a linear function, but linear approximation is like, it's close. It's linear and it's close to my function. Okay, so it's just different notations, but they have the same expression, and they sort of emphasize a little bit different aspect of the same thing. We use this linear expression to represent, approximate the real function f. But again, it only works well when your point is very close to the P, where the tangent plane touches the curve. The surface. Okay, example 3, find the linearization of f of xy equals x exy at 1, 0, and we're going to use the linearization to estimate f of 1.1, negative 0.1. So as you can observe, 1.1 is close to 1 and negative 0.1 is close to 0. So our points are not too far away from the point that we're estimating, 1.1, negative 0.1, is not too far away from the point we are computing the tangent plane, 1, 0. Okay, so let's compute it. I need f partial x, which will be, well, I'm having x times exy. This is a product rule. Taking derivative of x, I'm having 1, so it will be 1 times exy plus x times the derivative of exy will be first, derivative of e will be e to the same exponent, followed by the derivative of the exponent xy with respect to x, that's y. And that is exy plus xy exy. Now I plug in my 1, 0. This will be e times 1 times 0 plus 1 times 0 times e 1 times 0. Well, 0 times anything give you 0. I'm having e to the 0th power, which is 1. Now f partial y will be, well, easier. X is the coefficient. Then you just take derivative of the e to xy, same thing. E to any power is, first you have e, the power itself, then followed by the derivative of the exponent xy with respect to y. So this time times x. So I'm having x squared e xy. Plug in my 1, 0. This will be 1 squared e 1 times 0. So it's 1 times e to the 0th power, which is 1. So 1 times 1, still 1. Put them together in my linearization. Did I say linearization or estimation? Okay, linearization. So I'll call it L. So Lxy would be the output, which I didn't do. So f1, 0 equals 1 times e to 1 times 0. That's again 1. So 1 for f of AB, or f of 1, 0 plus f partial x, which is 1, times x take away the x coordinate of the point, 1, plus f partial y at the point is also 1, times y take away the y point, 0. So this is 1 plus x minus 1 plus y. Oh, this equals x plus y. Then we're going to use it to approximate f of 1.1, negative 0.1. That would be x plus y. So 1.1 plus negative 0.1, 0.1, sorry. And that will be 1. That's our estimation. Okay, that's our estimation. As I put in my remark, if you really compute the value actually f of 1.1, negative 0.1 would be 0.98542. Well, not accurate, but I stopped at the 5th digit and close enough, right? Not too far away. And that's how we use the fact, when you have this formula, probably with a z on the left-hand side, as the tangent plane at a point of the surface, so we can sort of replace, we can use the value on the plane to replace to represent or estimate the value on the surface. Okay, or in particular the z coordinate. Okay, now you can finish the practice number 2 and number 3.